Good evening. We live in a world where knowledge is the greatest power. As far as medical technology is concerned, the most important subject for this knowledge is ourselves. Now, these diagnosis techniques can easily be split into two categories: chemical and visual. The former includes teenage scientist Jack Andraka's pancreatic cancer test and entrepreneur Elizabeth Holmes' new 30-in-1 rapid blood analysis. The latter is what I care about. The use of digital image processing to dynamically identify and match physical indicators of medical issues. On a macro level, this can be the remote analysis of pictures of eyes being facilitated through mobile devices in the developing world. On a micro level, we have the focus of our research here: algorithmic cytopathology, and similar analysis of other sorts of radiological measurements. As a starting point, let's consider AutoPath, now known as a combination of a variety of products by BD, a massive medical products company, including what is now known as SurePath, the preparation method, and Focal Point, the actual analysis device. So what actually does AutoPath do, or today SurePath and Focal Point? Well, they're a re-screening mechanism for pap smears, which, as you may know, are the primary method for the diagnosis of cervical cancer. Now, when I say rescreening, I do mean to emphasize that these technologies are not a replacement for cytopathologists. Instead, they use a variety of parameters, largely morphological, and also color-based and so on, to determine which regions on these slides have a high likelihood of the presence of either precancers or cancerous cells. Now, beyond that, they also identify for cytopathologists which slides out of a vast batch have an especially high likelihood of having this, to reduce the amount of time that it takes these cytopathologists to process through their massive amounts of samples. Now, the real problem being solved here is the fact that each of these samples, as many of these cytopathologists and the developers of these technologies will cite, have very, very, very few cancerous or precancerous cells, suspect cells, for the vast number of other cells in any given sample. So this results in a high number of false positives because it's very hard to distinctly say there are absolutely none here. Now, what this meant was that in the development of AutoPath, not only was there a necessity for a very specific and large-scale algorithm, which in this case depended on decision trees, a vast number of them, but also a very specific imaging system, such that you could easily filter accurately and consistently these images for noise and focus on what you actually need to know. The way this filtration occurs is through the determination of an average size, or at least range of sizes, for precancerous and cancerous cells from a given sample. Now, using these thresholds on either side of this range, it is possible to eliminate from an image, based on the determination of individual cells, all cells that are larger than or smaller than, or for that fact, any other materials that are larger than or smaller than the cells that you need to see to diagnose the presence of these precancerous or cancerous cells. These filtered images are then passed through a set of decision trees, which are a form of artificial intelligence. These decision trees sort these samples based on a wide variety of factors, primarily in the case of AutoPath, two things. The first, the ratio of nucleus to cytoplasm, which is useful because precancerous and cancerous cells have a tendency to have a significantly higher ratio in this case, both because of irregularity of nuclei and because of polynucleation. Secondarily, these decision trees look for hyperchromasia, a color factor that also designates precancerous or cancerous cells. Using these factors, the current form of this focal point, the slide categorizer that we saw earlier, gives each slide a score, which then allows the cytopathologist to determine automatically whether or not there's a high risk of presence of precancerous or cancerous cells within a given sample. Now, with the primary intention of this research being to identify alternate applications of the technologies pioneered by AutoPath to other segments of healthcare, I decided to look at a few other companies that have implemented these ideas. Now, the first of these was Deuce Technologies in the late 1990s, which created a system called Rapid Screen RS2000D that aimed to apply the same ideas as AutoPath to the detection of lung nodules. So first off, the situation for lung nodules is very different, primarily in that it is in 3 dimensions. In order to address this 3D nature of the environment in which these lung nodules exist, Deuce Technologies went about creating a more flexible system for both the filtration of these images, X-rays that is, and the identification of suspects. So in order to do this, it individually identified the possible range for suspects in any given context. And this allowed for more probabilistic consideration of what could and couldn't be a suspect, differing based on, for example, the size of the specific context in which it is used. Now, the other interesting issue addressed by Deuce Technologies concerns a significant factor in the identification of lung nodules that are potentially cancerous, which is sphericity. So just as the shape of cells in the context of AutoPath is important, because the more irregular a cell is, the more likely it is in certain contexts to be cancerous or precancerous. The more irregular the 3-dimensional shape of a nodule is, the more likely it is to be cancerous. So, aside from this specific issue that was solved, the other thing that Deuce Technologies demonstrated was that it made the actual identification classification more efficient through the use of neural networks as its artificial intelligence system, rather than decision trees. So what this is an example of is, as the other couple examples that we'll consider, it showed that it is possible, it has been possible, and continues to be, to make this process more and more efficient until it may be implemented in very resource-limited areas, environments. So before I move on to my final example, that was the question I asked Dr. Larry Rystrom, a friend who works at Life Technologies in Bothell, a company that builds a system called EVOS, which is a microscope system that attempts to digitize a number of the possible uses by biologists, such as cell counting, identification of whether a given sample is dead or alive, and many other situations. Here he is.
So the most interesting thing to me from our initial discussion a while back, was really the drawbacks of even the current development that's going on with technology involved with image processing of cytopathological samples. So would you be able to give me a quick explanation of some of those problems and possible solutions and so on?
Well, the problems are memory. There's always endless demand for images and memory, and you're pretty much limited by that. And then you may also be limited by, well, how long am I willing to wait? An hour, 15 minutes, 5 minutes, 10 seconds? In the counting microscope I showed you, the specification was it better count in 10 seconds or less, even though the processor was underpowered.
Now, quite in contrary to what Dr. Rystrom states, much of the current research that is attempting to increase the efficacy of these technologies is unfortunately increasing the amount of data that is necessary to store. Now, the primary of these that I researched is a technology called flow cytometry, which rather than analyzing large groups of cells, attempts to create a physical system in which individual cells are independently analyzed, such that it is impossible to simply miss cells, as was often the case with AutoPAP. So this disparity kind of leaves us hanging because it means that until technology as a whole becomes cheaper, we really don't have a way of implementing our perhaps even more effective technologies in the future in these resource-low areas that we previously discussed, like the developing world. So, to give us at least some sense of closure, here's Dr. Rystrom once again talking a bit about what the future of the industry looks like.
Oh, I think we'll take advantage of parallel processing, being one of the big changes.
Cool.
Continue to use mathematical morphology.
So what this really brings us back to is that the technology as it exists is a great framework for what can occur in the future. Every year, the usage of SurePath and Focal Point increases, and though it still isn't yet accepted as a universal replacement for cytopathologists, it certainly has the potential to do so as AI's increase in capability, and continually, should it, for example, become cloud-based, even more feedback enters it, and it becomes more and more through machine learning a replication of a cytopathologist. So what this means is that, ideally, a system like that could be combined with continually advancing mobile technologies to really implement this on a smaller but globally centralized tool to be used for pathology universally. I'm Akshay Chalana, and thank you for watching.